Kishida from Quantinuum, and I'll be discussing about the mainly hardwares, but I would like to cover the recent topics, so updates from Quantinuum. And originally, this is the slide about our company in 2021, and the algorithm or the Cambridge Quantum, and also the Honeywell, the quantum solutions, and those two entities has been combined. And then we have a subset companies and science-led, enterprise-driven, and that is a slogan. And competitiveness, the meaningful use case. And with that, when we would like to commercialize or realize the quantum computing, and we are doing the research every day. And as of now, in globally, and we have over 400 of the employees, and most of them are the scientists or the engineers. Office itself as UK, and that will be the based in the UK, the Cambridge Quantum, and then also the Honeywell, and that is in the US office. In addition to that, Germany, as well as in Tokyo, we do have the offices. And this is a Quantinuum, KK, the Japan, and in 2019, it has been established, and last year we have changed to the Quantinuum from the Cambridge Quantinuum, and that's located in Otemachi, and not just the cells, the force. However, we do have the R&D capability as well, and in Japan, and we do have our own the research as well as the research with the customers, and as you see here. And last year, with the Mitsui and Cope, and we made an announcement that we became the strategic the partnership, and in Japan, and then also the APEC, and we are focusing on the expanding our business, and we're actually hiring people. And what we do, which I would like to talk, and from hardware and the middleware, hardware at the bottom and the middleware, and then also the software and the algorithm, and those are the stocks, and hardware and the middleware and the software, and that's what we covered, and we actually do all of them. And hardware itself, ion trap type, and the quantum computing, and which I would like to talk about it, and which is the 8 series, and ourselves. The middleware ticket, and we developed that as well. The ticket itself, the creating that the circuit for the quantum, and then bring the tasks, and hardware neutral, and for any hardwares and the platform and simulator, then we support. And therefore, if you use that ticket on, and in the case you can use IBM or AWS, and you can bring the task into. And on top of that, the ticket, and as many software and algorithm can be developed, and cybersecurity, that's one. And the other one is a quantum chemistry. And other than that, AI and ML. And in this way, and from hardware to software, we covered everything, and we do our own laboratories. And also at the very top, and there's the industrial and academic collaborations. And today, among those, and there's many things, however, the time is limited, and therefore, I would like to talk about the H series. And the hardware, the quantum charge coupled device, QCCD, and this is the architecture that we applied, and the ion is trapped, and ion trap type of the quantum computers, and that's what we do. And in the blue, and this is the gate zones, and in order to control the gates, and we have the gate zones, and physically that the qubit is going to be located, and then be able to calculate, change that the status. And for this the qubit and isolated environment that we are going to provide, and therefore it's very clean and fidelity is quite high, and that is the uniqueness of a solution. And here itself, the qubit and volume, and this is so all of the bit is the equal or the uniformed. And let me talk about the architecture further, and let me use this the drawings, and there is 3, and the 3 qubit with the different colors, red, green, and blue. And this is one of the example. And we need to initialize, and that's what we're doing here. And at the gate zones, and for each them, and we apply the lasers. It's going to be 0 at the beginning, and then for the blue and the green, we are going to focus on that. And for each of them, the red and green, and that bit is going to be bring to the gate zones, and then with the lasers, so 0 and 1 superposition. That's what we can get. And the next is going to be pretty easy, clear, and the green and the red, and we would like to entangle and the green one. And in the same way as the red, we are going to bring that to the gate zones, and with the laser, and we do the entanglement. And in this way, physically, we move the location of the ion and calculate it. So this is isolated and clean, and high fidelity can be maintained in this way. And the next, and the third, and the green and gray and blue entanglement. That's what we would like to do. And the way would be the green and the red is going to be physically swapped, and we change that alignment. And then after that, the red is going to be brought to the blue gate zones, and with the laser, and entanglement can be done. And at the end, and the green one is going to be measured, and we would like to get the result. And the green is at the isolated at the gate zone, and the ball with the lasers, and we just do it. And then what is interesting here is that this gate itself is isolated. And again, the green for the green bit, if there's a lasers, put it onto, and then you can actually use it, and with a high fidelity. So reuse is available. So that's the first thing. And moving that ion, and we'll be able to connect. And that top qubit, and when we entangle that, and the multiple swap does not need to be done. And as you see here, and for the ion, it's an isolated environment, and that's been built, and therefore the high fidelity can be maintained. And the other uniqueness will be here. As you see here, RZZJ and ZZ phase Z, and that it can be supported. And what is good about it is that C0 gate, usually, with the RZ rotation and C0 rotation, with the circuit, the C0 that you have to do it twice. However, with the RZZ, and you don't need to do twice, just one time is required. So the gate numbers can be reduced. And depending on the theta angle, the error, the volume is going to be reduced, and therefore the theta is less, and then for the noise, it's going to be strong. And that is the benefit. And as I have said, in the middle, you can measure and then reuse, and that will be available. And then, depending on the outcome of the measurement, and you can actually select do the gate operation or not, and that kind of the logic can be available. Now, for this H1 in 2021 and 43, the papers has been actually released, and in 2021, and that's been the 3 times more compared to 2021. And among the 43, and of course there is our companies, and also the user companies, and also the partners, the collaboration, the papers, and that is included. IBM is one, and Microsoft, and JP Morgan Chase, and many enterprise are included here. And there is several, the customer's voice, and they really like it, and it can run, and result is good. And the best NISC device, and those are the one of the comment that we hear. In terms of functionality, mid-circuit measurement reuse is available, and it's quite few that is available. And then also because they reduce the hundreds of the gates due to the all-to-all connectivity. And I did not really talk about it. This noise model is used, and for the elevator has a high faithful characteristics. And as you see here, and this is the first generation H1, the quantum computers. And there's a traps that you see on just on the line, and you place the ions, and then you will run this and calculate. And then 20 fully connected qubit and the 5 parallel gating zones available. And as I have said many times, and high fidelity and error rates are shown in here, but high fidelity is available, as you see here. And if this that's on the GitHub. and every month it's released and published, and it's updated all the time. And the numbers, and this is as of the 15th of the June, and that is released on the report, and that's been publicly available. And this is the review of what we do. And QCC, the architecture is used, and then ion trap machine is that is our the solutions, which is the all-to-all connectivity. And now, I'd like to discuss about and how we will be able to scale out. And in May, and this is what we have launched, and this is the H2, and this is the next generation, the new model. And please take a look at this, the photos and ions, and this is in the restruct type, and as I have said, high fidelity, and then also we will be able to do that fully connected, and the qubit number has been increased to the 32, and you will be able to confirm, and because this is publicly available data, please check. And this is the racetrack, and in this way, on the ions, is actually running in this way. And there is animations at the bottom, and this is the ion moves, and the 32, the qubits is moving. And gate zone itself, and at the both side there's a 4 each, and as of now, and this side, on the only one side, and there is going to be a operation at the gates. And with the high fidelity can be maintained, and at the same time, we launched the H2, new generation solutions, and we do have that many the benchmarking and quantum volume the measurement, and that's in the papers, and on the archive it is available. If you want to see the that and archive, and please access to that. And next, and this is a new topic, and what can we do with the H2? As anything new is available, and those are the sort of examples of applications. And the left-hand side, and using the H2 anion, so-called anion, as a special type of the physics, the status, and we have done that simulated in Munich team, and then also Harvard, all the Caltech members, and we have collaborated in this research, and the paper is available. And this is very scientific, the papers. And other than that, the middle ones, and this is the optimizations for the algorithms, and we can use that H2 and by AKPP, and this is the new the algorithm for the combinations, and using this. And for the H2, 32 qubit is used, and calculate and solve that the problems, and that's what we have done. And certain numbers and several hundreds, and with that, and we can solve the problems with this. And the last one, the right-hand side, and this is the benchmark, and that's actually in the papers that I have talked about, max cut and QAOA circuit, and mid-circuit measurement, and using that characteristics. And then 32, there's only 32 qubits, however, in the middle, and we can reset and reuse. And therefore, 130 qubits equivalent, the problem will be able to solve with this. And in this way, H2. H1, which is a line, and also H2, and this is a racetrack type, and that has been released recently. And this is a roadmap after that, and that's on the website. And in this way, we would like to scale up, and we would like to scale up further. And at this time, and what is important would be how we can increase the performance, and that is going to be the key. And in order to increase the performance for the phototoromet, not just increasing the qubit only, however, we have to maintain the fidelity or higher fidelity. It would be very important, and also with more the qubit and more the bigger the problem should be solved, and that is going to be the important. And then the qubit, the computers, the boundary can be wider, and that is very important. That's what we think. So in this way, we are going to improve. And with the first models, like the H0 launch, and that was 2020, and in the next 5 years, and we are going to actually increase the one digit or the 10 times improvement, and that was pretty challenge. However, this is our target, the improving that 10 times per year in terms of the improvement. And we have done this in the past years. And in a recent 6 months, it's been like 30 times more that we can increase that improvement and improve the performance. And this kind of the calculations, and we have done the tuning, and the machine is shut down, and then do the tuning and calculations. We did not do that. And all the data, actually, between the job of the customers, we put it in that. And then we got this outcome. And therefore, this outcome or the performance data itself, that is actually that the customers can use. And now, how you can access to the H1, H2, and this is shown in the slide. And simply, if you want to try, in the case, on a Microsoft Azure Quantum, and on that, and H1 and H2, you can access to it, and you can use it, and that is going to be one path that you can select. And other than that, there's other path, and there's a package which is an Inquant that we offer, and as options, and there's a hardware H1, you can access to it. That is another way. And then also there's many tasks if you want to continue to do so. And in the case, if you can access to our the platform directly, and then that is going to be other path. And for the details, and please check on our website. Up to here, I've talked about the H1 and then also H2, the next generation. And lastly, I would like to talk about that another topic. And recently, we have actually released the papers, and which I would like to summarize here. And this shows that on our device, and there's an error detection, and phase estimations using those two, and energy calculations of that hydrogen moleculars, and that was the paper about. And based on that hydrogen the molecular, and we calculate, and using that Bayesian QBE, and with the error detection code, we do the encoding, and then on top of that device, and we put that on the device, and we run this. And periodically, we have to check the errors, whether there is errors or not. And if we find the errors in the case, and we have to cancel this, and we have to start over this, the test. And if there's no errors, direct at the very end. In the case, we will use that result, and based on that, parameter is updated. And once again, we are going to run this cycle. And we repeatedly do that. And then, not WQ, but phase estimation, and that is the methodologies, and calculate that molecular. And using this error detections, with that error detection compared to that, and how the accuracy can be achieved. And this research itself for Japanese scientists were actually working on this mainly. And at the end, now in terms of this error detection, tomorrow, and our the senior research scientist Demeter Mara is going to talk about it tomorrow. If you're interested in, please come to this presentation. And then also at the very beginning, as I mentioned, and we're working with the Mitsui Bussan, and who is the partners, and they are going to be in a panel discussion regarding the sustainability and smart city. And if you're interested, please come. And we cover the hardware and software and everything. And then also the recent topic is going to be H1 performance is actually brought into the H2. The new H2 is released, and then also the cyber, and also there was other area I did not talk about it, but H1 on the software side. If you are interested in that case, please come to the booth. Thank you very much for listening. That's all. Thank you. Thank you very much.
Maybe 少し時間がありますので。
If there's any questions, please raise your hand.
質問をお持ちの方はいらっしゃいますでしょうか。はい。
Please write. Thank you very much. The cloud base. I would like to use the cloud base. And in that case, Japan time. Can we apply the Japan time? A time zone. That's a good question. In the morning, yes, that's available. And but there is a downtime, right? Yes. And basically, that's H1, H2, and that's in the United States, basically. And U.S. working time a little bit longer than that. So in the morning, it will be available, I think. And of course, there's lots of queues, and therefore, whether it can be run real time, process in real time, maybe not, because there's lots of queues. But in the morning, that will be available. You can run. Thank you very much.